Hey there everybody, this is a video for my 30S Pre-Cal honor students, and hopefully this is about where you are at. I left you with an in-class activity the other day where we generated all of the coordinates to go all around here and left you with a blank one, and I said see if you can fill in everything you know about this thing without peeking back, or peeking back as little as possible. That includes telling me all the angles all the way around. All the way around. It means filling in all of the coordinates all the way around. It means filling in the fact that there's a cast rule, C-A-S-T, and that you put the coordinate values here. And don't forget the 90-degree family, which we kind of tacked on the end of the last 1 hour ungodly long lesson. So yeah, this should be ready for you to use to solve problems and answer questions. And there will be some in the homework coming up, but there will also be some questions like this lesson here. Not there. No, not there either. This is a blank page that is of no use other than it is blank. See outcome T1. Oh, that's very nice. Okay, so here we go. Let's get this zoomed in a bit and maybe moved over a little bit and down, and there we go. Ready, set. By the Pythagorean theorem, suppose any angle in standard position and pxy is any point on its terminal arm at a distance r from the origin. By the Pythagorean theorem, you know the distance that it is from here to here. This you could call it a radius if it was part of a circle, but you could also just call it r. You could call it c if you want to go a squared plus b squared equals c squared. We'll stick with r because, again, we're always thinking about this as part of a circle, so r stands for radius. And this r is going to be the square root of x squared plus y squared. And recall that we know three trigonometric ratios, sine, cosine, and tangent. And we can now rewrite these in terms of x, y, and r. So the sine of theta is y over r. The cosine of theta is x over r. And the tangent of theta is just y over x. And these are on your formula sheet. If you're wondering, hey, my formula sheet doesn't say the opposite adjacent hypotenuse stuff. It says these weird letters. Now you know why it says them, because we're thinking about this as part of a circular function. Then it says, carefully read the table on page 90 of your textbook. Do it now. My word, these are very demanding notes. Well, I didn't give you a textbook, but I can show you that your textbook is linkable here, and there's really, this page is not all that exciting, to be honest, but apparently we have to do it now. So go to your textbook, which is, here it is, grade 11 pre-cal textbook can be downloaded here. You don't even have to download it, you can just open it. And I think it's probably at that page because I went and checked it just a few minutes ago. Because I was like, what's so important about this page? And it's like, oh yeah, here it is. Here is kind of a summary of everything we can do with the quadrant rules and our new formulas. You see, the quadrant rules say that if you're in quadrant 1, and notice this is a big grid, so this is quadrant 1. In quadrant 1, it's the three formulas I just told you. Sine is y over r, cosine is x over r, tangent is y over x. And in quadrant 1, remember that sine, cos, and tan, the A of the cast rule, A standing for all three of them, have to be positive. So this is actually one of the answers to this question. Why is r always positive? How can we think about x's and y's as being negatives, but we never think of the r as being negative, even though sometimes it goes towards the negative directions? Well, for one thing, we can't mess with the fact that these rules for sine and cosine and tan have to stay consistent. So we couldn't arbitrarily say, oh, sometimes r is negative, because it would mess up these rules in the cast rule. Secondly, this is a little deep maybe for this video, but technically speaking, distances are never negative. And you're going, well, wait a minute, this distance right here, you're calling it negative. Actually, I'm kind of not. I'm saying that this is the negative x so that I can get this coordinate. The coordinate on the grid is negative. The actual distance is just x, which is going to be a positive number, but I'm taking x to a negative direction so that I can give it a negative coordinate. So I know that kind of sounds like a technicality, but technically the distances aren't really negative. It's just their coordinates on the grid that are negative, and we never make a diagonal line or any line really have a negative value. So the lines, in fact, are all positive. It's just their coordinates that are negative. And when it comes to the diagonal itself, well, it takes two coordinates to tell me the diagonal, and one of them is, in fact, negative. So, haha, r is always positive. And remember that in quadrant 2, it's still the same three formulas, but this time cosine's negative and tangent's negative. In quadrant 3, sine is negative, cosine is negative, but because you have a negative divided by a negative, tangent is positive. And in quadrant 4, if you had a triangle stuck down there, sine's negative, but cosine's positive because the x is in the positive direction, and tangent is negative. So, good thing we checked that page. Just remember, if your notes ever do that to you again and say, go to the textbook, you can always just go back and find it from the blog. All right, back to notes. Example 9. Determine the exact values of sine, cos, and tan for the angle whose terminal arm goes through the point 2, -5. What do we mean by exact value? We mean you don't get to play. So here we go. Let's draw a little sketch. Where is 2, -5? Well, that's 2 in this direction and 5 in that direction. So 1, 2, 3, 4, 5. So there's point P. Oops. I don't know why I made an extra bracket there. P of 2, -5. And let's make a triangle to it. Triangle from 0, 0. And now let's make a reference angle. And here comes my reference angle right there. Haha. So find the sine, cos, and tan theta values right there. So according to my formula, I need r for sine and cosine. So I am going to find r. R is going to equal the square root of 2 squared, add -5 squared, and it's kind of important you put that negative in the bracket. R is going to equal then the square root of 4 plus 25, and R is going to equal the square root of 29. Well, there we go. Isn't that nice, the square root of 29? So the sine of theta, which is of course y over r, is going to be, well, let's see, it has a y coordinate of -5 and an r value of the root of 29. Cosine of theta is x over r, which is going to be this x distance, which is 2 over the square root of 29. And tangent of theta, this is the one I could have found actually without doing the r, because there's no r in this one, it's just y over x, which is -5/2. Now, that's it. That's the answers. Those are the exact numbers. If a question wanted you to find how big the actual angle is rather than just the sine and cosine and tangents of the angles, yeah, you're going to have to bring Mr. Calculator back into the fold, find this decimal, and then do inverse sine, inverse cos. We'll look at examples like that in a minute. And the next thing maybe I should point out is, you know, some textbooks don't like that answer. I'm actually perfectly fine with this as an answer, but remember that some textbooks like to do that whole rationalize the denominator thing, because again, we don't like having denominators as radicals. We kind of consider it an improper answer. So you would actually just times by this, and you'd get -5 root 29 over 29. So I'm pretty happy with that as an answer, and certainly when you're doing your homework, do that and stop there and look in the back of the book and say, yep, that's the right answer. But if the back of the book looks like this, hopefully you can figure out how to go from there to there, because you learned how to do it back in grade 10. And if you can't remember stuff from grade 10, what are you doing here? No, I'm sorry, that's me, sorry. All right, what's next? Well, if it was example 9 before, it's example 10 now. Given sine of theta is 2 over root 7, and its theta is in quadrant 2, determine the value of cos and tan. And again, we should probably have said exact, because yeah, I could put that in my calculator, get a decimal, do the inverse sine of it, then I have an angle, and then I could find cos and tan. But I want the exact numbers. As soon as I start using my calculator for the root of 7, and not to mention sine, I'm going to get irrational numbers. So what do I know about sine? Well, sine theta, whoops, sine theta, sine theta is y over r. So I can draw you a little picture. I know I'm in quadrant 2, which is over here. I don't know why I drew all this much. I don't need any of that. But I'm in quadrant 2, which is over here. And I am root 7 for the length of my hypotenuse. I honestly don't know how big. What is root 7? Well, the root of 4 is 2, and the root of 9 is 3, so it's somewhere between 2 point something. So 2 point something takes me out to that. We'll say there. So that's my hypotenuse, is root of 7, and my height is 2. Now you might be wondering, why did they bother telling me that I'm in quadrant 2? Well, because notice I could have put the same triangle over here. It would have still been a positive for y, and of course, you know, hypotenuse is always positive. So there is, if I just give you that information, 2 answers. But as soon as I give you that piece of information, that it's in quadrant 2, aha, now I only have 1 answer. And I would like to know the cosine and the sine. So I'm going to run through cosine. So the cosine, I'm going to need to know this x number, right? Because I need to find x comma y, and I know y is 2. So the x value is my cosine value divided by r, of course, right? So here we go. I'm going to find cosine's x value. So x squared plus 2 squared equals square root of 7 squared. It should make logical sense to you that square root of 7 squared is just 7. And so x squared is going to equal 7. This is 4, so 7 minus 4. So x squared is going to equal 3. And finally, remember back when you did Pythagoras in grade 8, and some of you probably knew, oh, when you square root both sides of an equation, you have to think that this number is plus or minus. Well, your grade 7 teacher probably said, well, yeah, but this is a distance of a line. It doesn't make sense to call it negative. Well, now, the distance is still positive. We just talked about that. But the direction that distance is going on the grid is negative in this case. So when I square both sides, I have a choice between plus or minus. Think about why that is a choice. What number times itself is 3? It could be positive root 3. It could be negative root 3. And in this case, I want negative root 3. Why? Because this line's over here where x is negative. And cast rule says that sine is the only thing positive over here. I know cosine has to end up negative. So the cosine of theta is negative root 3 over root 7. Now, I'm again happy with that as an answer. If you stopped there and gave me that as an answer, I'm totally fine with that. But it might say in the textbook this, and I don't really care. They're both the same answer to me. Okay, not really a preference there. I kind of like this one, to be honest. Tangent is opposite over adjacent. And I just found out that the adjacent is negative root 3. Some people will tell you that you should always put the negative either in front of the entire fraction or on the top. Doesn't matter. And again, a textbook might simplify that radical by rationalizing the denominator. So I'm happy with either of those answers. Actually, I wouldn't even take off any marks if you left the negative down there. That's fine by me. I'm not all that picky when it comes to these, as long as the answers are exact. No decimals. And that's it for that question. Very nice. All right, now one that actually involves an angle. Point PXY is on the terminal arm of theta equals 35 degrees. Okay, what are we going to do here? Well, let's see. The distance r between P and the origin is 8 units. To the nearest tenth, find the coordinates of P. All right, so let's draw that. We are at a terminal arm of 35 degrees. So that's a terminal arm, so that's like, I don't know, there. 35 degrees, something like that. And we know that r here is equal to 8. So what do we know? We know that we know that this is the y number, that's the x number, and we know that the sine of 35 degrees then is opposite over hypotenuse. And finally, we've hit one where we're going to need our calculator, because is 35 degrees on our unit circle? No. Boy, wouldn't it be nice if this had been 45 degrees? Because if this had been 45 degrees, I'd just replace this number with root 2 over 2. I'd move the 8 up there, cross multiply, boom, I got your y value. I didn't need my calculator, but 35, that's not on my unit circle, and that makes me sad. Okay, calculator, you can come back now. We need you. What is the sine of 35? Actually, let's rearrange that first. I like punching all my buttons at once. Y is equal to 8 times the sine of 35. I'm sure this is the way most of you learned how to do trig in grade 10. So let's see. Let's punch that in the calculator. Y is equal to 8 times the sine of 35. And always make sure you're in degrees, right? Dig it. And that looks like it said, now to the nearest, what did we want it to? The nearest tenth. So that's 1 decimal place, so we're looking at 4.6. Do we have a unit here? Units, didn't say. And what else do we need to know? We need to know then that the cosine of 35 is equal to x over 8. Same algebra, different trig function. 8 times cos 35. 6.6 units. You don't have to write that. If it doesn't give you a unit, I don't really care about it. And so that means, now here's the part that's interesting. Remember that that means that this coordinate is x comma y. So actually, my coordinates, and I'm writing off the screen, sorry, my coordinates of theta, or pxy, as it's said up here, pxy, is in fact this number, 6.5, and this number, 4.6. La. Isn't that nice? So there we go. That's how you do a question like number 11. Okay, we're going to keep rolling. There is a little break in the booklet here and a textbook assignment, but there's really only kind of one more little lesson here for the road, and this will only... Oh, and I'm frozen. I moved my pages too fast. Help me. Oh, there we go. This will only take a couple minutes, so let's just let's cruise our way through it, shall we? So we are looking now at, it even says example 12. We're going to start with an example. We want to solve for theta when theta is between 0 and 360 degrees, or there it is in interval notation from 0 to 360 degrees. And this is the equation we want to solve. So it even tells us the steps. This is really nice. Step 1, isolate your trig function. In other words, just treat sine of theta like x. I want to solve for x, so I want to move the 1 to the other side. So that'd be 2 sine theta minus 1 from both sides, so that's equals -1. And then sine theta is equal to -1/2. There. I have isolated the trig function. Now, here's how you have to do this. You have to think about what the reflection, blah. You have to think about what the, oh my word, I'm having some sort of problem saying the word that begins with R. The reference angle. Sorry, my word. You have to find the reference angle, and you do that by worrying about the positive ratio. In other words, don't worry about the fact that sine's negative. Just worry about the fact that, hang on, where is sine 1/2? So just ask yourself the question, where is sine of theta equal to 1/2? In other words, in quadrant 1. Because remember, reference angles are always acute. So in quadrant 1, I got to think, oh, I could go back to my beautiful unit circle if I could find where I set it down. There it is. Where are you, 1/2? You are, the sine value is 1/2 right there, right? When the y value is 1/2. So that's 30 degrees. So I know that my reference angle is 30 degrees. Now, because sine's negative, I use my cast rule, and I decide that, wait a minute, sine isn't negative here, sine isn't negative here, sine is negative there and there. So I actually put my 30-degree angle down here and my 30-degree angle down here. Now remember, those are reference angles. How much are they when you figure out the standard form angle, when I go around that way and when I go around that way? Well, my two answers are, when I'm in quadrant 3, my quadrant 3 answer would be 180, here I'll write it down, plus 30, which is 210 degrees. And in quadrant 4 over there, that's a Q, my quadrant 4 answer would be 360 minus 30, which is 330 degrees. And that's my two answers. When I solve this equation, I get two answers. That's not the freakiest thing ever. I mean, think about it. When you solve the equation, just using some scrap paper, when you solve the equation x squared equals 16, that gives you two answers because x could be plus 4 or minus 4. So in this case, there are two angles that would make this a true equation. And you can prove that. If you like, you could check your answer. 2 times the sine of 210 degrees plus 1 should equal 0. And the other answer, 2 times the sine of 330 degrees plus 1 better equal 0. Yep. There you go. Those are my two answers. All right. Why don't you try these three examples, but I'm going to give you a hint. Okay? The hint is that I don't think you can use a calculator for any of these. At least I don't. Let me look at it carefully. Yeah, these examples here, yeah, you need a calculator for all of these, right? None of these. Yep, none of these are ones you can do without a calculator. So you need to use a calculator for these, but remember, you've done stuff like this back in grade 10. It's like, oh, I know how to find theta. I just do the inverse cosine. You're right, you do, but remember that isn't there two places where cosine can be positive? Find both answers. Here, follow the steps we did up there, right? Step 1, isolate your trig function. Well, okay, that part's done already. But step 2, ignore the negative, find the reference angle, and then use the cast rule to figure out your two answers. Okay? So feel free to try those. Pause it for a sec, and then I'll go through them. Did you try them? Okay, so how did I know I needed a calculator? Well, because I know there's no 0.3s on my unit circle. So I know that my theta r is the inverse cos. Remember, that's the actual symbol you use for inverse cos. So that's going to be inverse cosine of 0.3. And I need a calculator for that. And I get 72.5 degrees. So theta r is 72.5 degrees. Now I'm going to make a little sketch. Where is cast rule? Where is cosine positive? Well, it's positive here. So that's 72.5 degrees. And it's positive here. And that's the reference angle of 72.5. Well, in quadrant 1, the answer for theta is 72.5. Remember, in quadrant 1, you are your own reference angle. But how big is the angle if I have to spin all the way around and hit it in quadrant 4? Well, that's going to be 360 minus the answer I just had. And I have an answer button, so I'm going to use it so I don't have to repunch it. 287.5 degrees. And there we have it. This one, okay, remember that theta r is the inverse cos of, drop the negative. Don't use a negative. Now there's people going, why can't I use a negative? Sometimes calculators handle negatives fine. Sometimes calculators in this situation will give you negative angles, and we don't want negative angles. Negative angles means you're going clockwise instead of counterclockwise around your circle, and that's going to give us weird answers. We don't want to think about that. So drop the negative, find theta r. So let's see, what is the inverse cosine of 0.34? Ba-da-boom. It's about 70.1 degrees. So theta r is 70.1 degrees. And okay, where is cosine negative? Cast rule time. C-A-S-T. Here and here. So there's a 70 degree angle there and a 70.1 really degree angle here. And how big is that angle and how big is this angle? Okay, well this one is 70.1 away from being 180. So the first one is 180 minus my answer. Sorry, I'm off the screen. So the first answer is 109.9 degrees. And then the second one would be 180 plus that. So I'm just going to actually I'm going to do 180 minus my answer again. There we go. So there's the first answer I had, 70.1. But now I want to add that to 180. So plus 180. And there we go. The second answer is 250.1 degrees. Next, where is the tangent of theta equal to negative root 2? Step 1, find me a reference angle. Inverse tan of root 2. Remember, drop the negative. Inverse tan of the square root of 2. There we go. 54.73. Okay. Where is tangent negative? Where, oh where has my cast rule gone? Tangent's negative over here and over here. So I have a 54 degree reference angle there, and I have a 54 reference angle there. How big is that? And how big is that? So this one is 180 minus that number. 125.3. And yes, notice I dropped the R because I'm not talking about the reference angle anymore. I'm talking about the standard form, standard position angle. So that's important. This is not theta R anymore. And the other answer would be 360 minus that 54. So I'm going to just take 180 and minus that number. And then I'm going to minus it from 180 or from 360. Did I say 180? Obviously all the way around is 360. So 360 minus that answer is, bada bing, 305.3. Okay. And you can once again check the answers, right? The tangent of this, tangent of that answer is negative 1.414 blah blah blah. And just to make sure, is that what root 2 is? You bet it is. 1.414 blah blah blah. So yep, it's right. You can check the other one too if you want, but I know it's right. Ah, they don't give me much room here. There we go. I like that. Divide it up. Hey, I finally get to do some actual algebra here. 3 tan theta minus 5 equals 7 tan theta minus 6. You know, to me, in my mind, this isn't really any different than 3x minus 5 equals 7x minus 6. It just so happens my x happens to be tan theta. And I deal with this the same way I deal with all grade 9 algebra, where x is on both sides of the equation and it's linear. I would just collect my like terms. So I'm going to minus 7 tan theta from both sides. So on this side, it's negative 4 tan theta. I'm going to add 5 to both sides, so this is negative 1. So the tangent of theta is 1/4. Is 1/4 one of the special things on my unit circle? No, it is not. So once again, I got to use my calculator. So I would like theta r to be the inverse tan of 1/4, which is inverse tangent of, I know it's 0.25, but I'll show you that, you know, fractions work too. 14.03 degrees, or 0.4, I guess, if I rounded it to 2 places. Cast rule, help us out here. Where is tangent positive, right? Because that's a positive number. Here, so I have a very skinny 14-degree angle here, and everything's positive in quadrant 1. So you are your own reference angle in quadrant 1, so 14.0 degrees if I round it to 1 place. And here, that'd be 180 plus 14, so that's 194.0 degrees. All right. Did doing these examples make you a little sad? I have to say, they made me a little sad because it was so exciting to be able to use the unit circle to not have to touch the calculator. So lucky for us, here's a couple of examples where it says, without a calculator. Now the first one, holy cow, that is a very easy piece of algebra. You just have to do that theta r is the inverse sine of 0, which is in fact 0. And then, okay, where on the unit circle is sine 0? Well, sine is 0 where the adjacent is 0, which is here and here. So I have 2 answers for this. I have the answers, that's going to be, well, here would be 0, and if I went around to here, that's 180. Oh, but wait a minute. I want to solve for all the answers between 0 and less than or equal to 360. Notice that little line under the less than? That means I have to count 360, so there's actually 3 answers. Theta could be 0 degrees. Sine of 0 is 0. Theta could be 180 degrees. Sine of 180 is 0. Try it if you don't believe it. Sine of 180, 0. And there's a third answer that is being demanded by the fact that I want all the answers in this range, and that answer is 360 degrees. And by the way, there have been times on the grade 12 provincial where this stuff pops up again in grade 12 where they won't put that little line under the less than, and you get used to including the 360 answer, and if that little line's there, that means it doesn't include the 360 answer. And oh, I remember having a student that was the only mark they lost on the whole provincial exam. Man, was that ever a cheap way to lose 100%. Anyway, why do they even bother saying this? Well, you know what? Think about it. If without some sort of domain restriction for how big theta is, I could spin around here forever and keep getting zeros, right? 0 degrees, 180, 360, 540, 720. I could spin around 10 times and say that theta could be 3,600 degrees. So there has to be some sort of a range involved. If they don't actually say it, you just kind of assume within 1 unit circle, what are my answers? But usually they actually do say what range they want you to use. All right, another one with some actual algebra in it. The tangent of theta, let's do it in 2 steps. 2 times the tangent of theta is equal to 1 minus 1, 0. Oh, that's not as exciting as I hoped. Tangent of theta is then 0 divided by 2, which is 0. And now where is tangent 0? Well, it's actually kind of the same places. Tangent will be 0 when I have 0 over 1. So that would be opposite over adjacent, so that's here and here. So, and again, that's the same answers. 0 degrees, 180 degrees, and 360 degrees. And there we go. All done. Those were really, really easy ones. They both involve zeros. I guarantee you some of these equations where you'll end up with things like root 3 over 2 in them. And you'll have to deal with 30-degree angles, 60-degree angles, possibly 45-degree angles. The mind reels. All right, go to the blog and check out which questions I'm assigning from your book. And that basically takes us to the end of 2.2. Next is T3, sine law. Thanks for watching.